So now that we have a foundation for how ionic compounds work, knowing how to interpret them, being able to name them and provide formulas, we need to specify something about a large group of elements we've been leaving out of the conversation. And that's what we call multivalent metals here. One of the first things we want to do to kind of illustrate this is by using this example of FeCl2 and FeCl3. So FeCl2, this is a compound that's been known to exist. And so one thing that they're going to ask you to do to start off with anyway is to identify what the charges are for the two ions present. As always, the metal is first and the nonmetal second, or the cations first, the anion second. So based on what we know from before, right, we know Fe. Fe is typically, again, a metal, or we know that to be a metal. So we'll look at the periodic table. And Fe, unfortunately, is not in these first two columns where we recognize their charges pretty immediately. So I don't really know much about Fe yet, but I do know some other information. One, I know that this whole thing overall is neutral. And I do know that chloride, right, if you look back over here, chloride is in a column where I know the elements or the ions have a very specific charge. So let's go ahead and walk through that process. So knowing this, I can kind of work backwards, starting with the fact that chloride is a -1. There's 2 ions in the formula unit of iron chloride, or this FeCl2. So I can go ahead and know that the overall charge is -2. Then, what about the positive side? Well, again, as the negative side has some charge, the positive side has to have an equal and opposite charge. So the overall positive charge for this compound is +2. And since there's only one iron, right, there's only one as a subscript there, even though it's understood not to be there, not shown, that means the individual charge of iron also has to be +2. So the combination here of FeCl2 yields the fact that Fe is a +2 ion and chloride is a -1 ion. And of course, just as a reminder, the things on the bottom here I'm noting as their individual charges, and what's on top is the total charge that those ions contribute. How to name this compound? So based on our naming rules from before, this would be named iron chloride, right? Again, we don't include any prefixes to denote the fact that there's 2 chlorides or anything like that, so it's just iron chloride. What about FeCl3, this next one? So this also exists. And so how do we break this one down? Well, again, FeCl3. Once more, looking at where iron is on the periodic table, we don't know what the individual charge of iron is, but we can work backwards and sort of piece it together. There's a little puzzle here, and let's look at Cl being a -1, right? We know that chloride is always a -1 charge. Go ahead and make the -1, triple that because there are 3 chloride ions, so -1 times 3 makes this overall -3. That means the overall on the left side, this positive side, has to be +3. So with that in mind then, what do we know about the charge of iron? Well, we actually can figure out that since this setup has a overall 0 charge, and there's only one iron atom, or one iron ion, that means it has to be +3 as well. So the next point here, how do we name this compound? Well, you notice here, again, based on whatever rules we've had before, we end up with the same name, iron chloride, right? Cation first, anion becoming an ide, being listed second. So we're coming to an issue where, what if I just gave you iron chloride as a compound on its own? Which iron chloride compound are you talking about? Are you talking about the iron with the Cl2 or Fe with the Cl3? I don't know. So this rudimentary system right here isn't enough to encompass everything we need to. And that's where we start introducing a new category of elements that we're going to work with called multivalent metals. So multivalent, let's go and break that word down. The word multi, of course, meaning multiple, many, and then valent referring to having valence electrons. This again goes back to the idea that, atoms will lose a certain number of valence electrons. Well, it turns out metals actually can have multiple possible charges because they can have multiple sets of valence electrons that they lose to become the ion. Now, how it actually works in those fundamentals, I'm not going to get into. We don't really need to know for this. But just know that there are specific elements with multiple possible charges, and we describe them as multivalent metals. Generally speaking, it's the transition metals and also those metals below the metalloids, right? So the stair step on the periodic table. So it's kind of like your Harry Potter metals. So all of these elements here, all of these right here, these are all of your metals. Again, these transition metals. And also the ones kind of underneath here, there's going to be a few exceptions, and we'll highlight those later on, and we'll at least address those later on. But for most part, all the stuff that I've highlighted here, all of these are the elements that are considered multivalent. So please don't use the cutoff here as a transition metal as something that doesn't need the multivalent designation. Furthermore, right, this also is technically included, so any of these elements that we ever come across, those are ones that you'll need to know are also considered multivalent. So then again, that's nice to identify them. Let's make sure we draw this comparison though to monovalent metals. So our monovalent metals, these are ions, or these are metals anyway, where they only have one possible charge. So all these elements that we talked about before, so all these in blue that I'm going to highlight, these elements here, all of these elements we talked about already, all of these always have a +1 and then a +2 charge. Whereas in yellow, all these multivalent ones, these have multiple possible charges, right? We don't really know them immediately just by their identity. Whereas over here, we know that lithium is always going to be a +1, or say potassium is always going to be a +1, when strontium here is always a +2, and magnesium. So in those cases, we know what they are. Those are monovalent metals. But the focus here on this lesson is about the multivalent metals. Let's go and see how this works. So what's different about this is a couple of things. One is that in the name, you notice you're going to have a cation, and very specifically now you're going to have Roman numerals and parentheses. All right, so Roman numerals and within a parentheses, referring to the charge on this metal. So this Roman numeral refers to the charge on that. Again, Roman numeral represents the charge on the metal for any multivalent metals. Like very specifically, not mono, multivalent metals. And then you have the anion listed afterwards, which has no difference in its system. Once again, there are no prefixes, right? Absolutely no prefixes in this. The formula, again, is effectively the same too, right? Because you always have a set of letters and numbers that sort of represent the elements and how many of them are required to form the compound. So nothing really has changed there. So let's go and take a look at these examples. All right, so the multivalent metal stuff that we just did, let's go and take a look at how FeCl2 and FeCl3 will be named. So first of all, the idea is that the first element, iron, hasn't changed. But what I'm going to do here is I'm going to go ahead and write out iron chloride and know that the name is going to have a Roman numeral in there. Well, if you remember, right, what exactly does a Roman numeral mean again? This represents the charge of the iron. Right, charge of the iron, not the chlorine. It has nothing to do with that. So in the name, what do we include here? We already figured out earlier that iron is a +2 charge, and so that means I'm going to write the Roman numeral 2. Of course, that's two I's next to each other. So this would be read as iron 2 chloride. You might also hear me say iron, specifically referring to the Roman numeral, iron Roman numeral 2 chloride. So this would be the most correct way to refer to a compound as as FeCl2. So that's how you translate these two back and forth. So this again does get translated to FeCl2. Please do note, and this is one thing I'm going to bring up now, and I want you to break this habit immediately, is that many of you, especially if you're kind of sort of not entirely sure how this works yet, you look at this 2, Roman numeral 2, and say, oh, you know what that means? That tells me that I have 2 chlorines. Right? And therefore, that 2 tells me that this right here is that same number. That is not the case. Do not do that. Big X's through these arrows where you might draw connections. Don't do that. Right? So the whole point of this is that the Roman numerals refer to the iron. So that means we don't relate the 2 with the chlorines that are there. So don't make that connection. Please, please, please don't make the connection. The second one, FeCl3, right? So again, it starts off the same way, where it's going to be iron, and then it's going to have the chloride. But now, because I know this is a multivalent metal, it's an iron, right? That's something that appears in the middle of the periodic table there. We don't know the charge just by looking at its identity, so we have to tell ourselves what it is. So this again is a +3, right? We've identified that from an earlier slide. That means we make this iron Roman numeral 3 chloride. So this again is your answer for how you distinguish between iron FeCl2 like that or iron FeCl3 like that. So iron 2 chloride or iron Roman numeral 3 chloride refer to two similar but very different compounds. And of course those Roman numerals refer to the charge on the iron. Couple of exceptions. So most of those elements that I highlighted earlier, if you look back to this guy, right, all these in yellow here, these are mostly, again, all going to be multivalent. There are a few important exceptions, and I'll highlight those in just a minute. So there are a handful of D block elements right here. So silver is always a +1. Zinc and cadmium are always +2. So even though, right, so finding where these are, let's go and highlight these real quick. I'll do this in red. So you'll find that silver, which has a symbol Ag, this one right here is always going to be +1. Whereas zinc and cadmium, these two that I listed a minute ago on the previous slide, these are always going to be +2. So even though, again, they appear to be a multivalent metal just simply by location, these are exceptions. So we don't actually treat these as multivalent. We, in fact, treat them as, instead, monovalent. And those don't get any Roman numerals, and there's not any ambiguity to it like iron would have. One more thing that's included is aluminum. Aluminum, this one is technically not a D block element, but it's important to specify it anyway. So you kind of see that, this is going to be +3, and there's a bit of a little mini grouping here. You can kind of see that there's a pattern. So with Ag, Cd, Zn, Al, all those right there sort of follow this pattern of being exceptions. So it's not like you're kind of randomly picking them out. You just have to memorize a little pattern there to know which one's considered mono or multivalent. And so one reminder, right, because these are all exceptions that require monovalent labels, right, they're not ones that have multiple possible charges, no Roman numerals are included. So you're going to have to know these charges. And so if you see, for example, zinc chloride, right, you'll say, okay, zinc I know is Zn, right, if you remember your periodic table and know the symbols, right, chloride is Cl, right, I got to know what those charges are. Well, again, you initially say, okay, zinc is here. Zinc doesn't fall into one of these known +1, +2s, but you'll have to remember that this is one of the exceptions. So zinc, in fact, is going to be a +2 charge. So that's +2. And this chloride is a -1. I have to put that together in a compound that is overall neutral. So then I can go ahead and come over here, make it ZnCl2 to know that there is a neutral compound, and going through the whole system, this would then have to be +2. This lowest common multiple would be at -2, and therefore I have to have 2 chloride ions. Here's some examples that you can run through just to see that you can put these together based on those rules. So these again are all monatomic, so we have single atoms that make an ion, but some of these are multivalent, or all of these are multivalent. So I want you to go and take this opportunity to produce both the name and the formula for the ion and compounds that they would form. In the next section here, this one has a few that are, they're not telling exactly what the charges are quite explicitly like in the previous one. So take a few moments now and try these out. This is going to be a little bit more of the types of problems that you'll see on an assessment where you have to go between names and formulas with not a whole lot of other prompts. So make sure you do take the time to figure out what it takes to identify these and then name them or provide the formula. So again, the prompting here says be sure to identify the type of compound, and whatever information will help you figure this out. Mixed practice here, so we've learned about a couple of different types of compounds, well, only one kind of compound, but different subcategories within them and how to address them, especially we're talking about the monovalent versus multivalent, so take the time to make sure you understand how to do that using this slide. And of course, a couple of error slides seeing whether or not you can identify some issues and how to see if you can correct them if possible. All right, that'll do it.